the mathematics of architecture, a study of the philosophy of emerging architecture. The presenter is J.K.B. John. The presenter was a student in civil engineering at Research General John Defense University. She is taking a graduation with first class honors. She is currently working at Unilever, Sri Lanka as a management trainee. She hopes for a career in the academic field, specializing in environmental engineering. So I invite you to do the research presenter.
Good afternoon, everyone. Permission from the chair, the panel, and all the distinguished guests. So my research is Mathematics of Architecture, a study of the philosophy of emerging architecture. Galileo Galilei said that mathematics is the alphabet with which God has written the universe. It has long been said that architecture is a game played with clear objectives but no guiding set of rules. Mathematics, on the other hand, has been described as a form of knowledge that is best understood as a game with a lot of rules but no clear objectives. Therefore, it is evident that architecture and mathematics are two distinct human endeavors. Yet both disciplines have their deepest roots embedded in geometry. One of the primary goals of this project was to explore the relationship between architecture and mathematics. The link between architecture and mathematics goes back to the ancient times. The first use of mathematics in architecture started early with the Egyptians in the design of the pyramids over 4,600 years ago. The enduring beauty of ancient architectural structures such as the Taj Mahal, the Notre Dame and the Parthenon is a result of the paradoxical combination between architecture and mathematics. So within the scope of this project, I attempted to understand and identify the mathematical principles used by ancient architects in the design of these ancient architectural structures. Today, mathematics continue to feature prominently in building design, and mathematics is more integral to architecture than ever before. Because of modern technology, architects can now explore a variety of exciting design options based on complex mathematical equations, allowing them to build groundbreaking forms. So the Disney Concert Hall in Los Angeles and the London City Hall are examples of modern architecture that display mathematical creativity. So a main part of this research was dedicated to understanding the non-Euclidean mathematical principles in modern architectural forms and to understand how architects have incorporated mathematical algorithms into their design. So there exist many phenomena in nature that can be described in the language of mathematics. Another part of this research was dedicated to understanding the mathematical principles in nature and how nature has designed its forms using mathematical principles and how we can incorporate that knowledge into architecture to improve its function and appearance. So Ron Iglash conducted an extensive research into ancient African architecture and he found fractals in their design. So this is a picture of the Baila settlements in southern Zambia. So as you can see, they form enormous rings. So they are made up of even smaller rings which are livestock pens, and they are made up of even smaller rings which are single cylindrical houses. So as you can see, towards the back of the village is another village, that of the chief's extended family. And if you consider each livestock pen, towards the back of each livestock pen is the family living quarters, and towards the back of each house is the sacred altar. So by looking at this arrangement logically, we can say that the chief's family ring is to the entire settlement as the altar is to the house. So in such settlements, the chief was considered as the father of the community, and this relationship has been structurally mapped through self-similar architecture. So within this research, first I studied about the mathematical concepts in ancient architecture. Then I studied the non-Euclidean mathematical principles governing modern architectural forms. So then I studied natural forms to see what are the mathematical algorithms incorporated into their design. So then I obtained a frangipani leaf and I studied it to understand the mathematical principles governing its design. After obtaining that mathematical algorithm, I tried to incorporate that into a structure. So mathematical principles in architecture. So if you compare the ancient architecture of the Greeks and the Romans with modern architecture such as the cybertecture egg in India and the bird's nest in Beijing, China, you can see that a great revolution of ideas separates ancient and modern architecture. This is because to the ancient Greeks and Romans, mathematics meant geometry above all, and the Greek view of geometry was the geometry of Euclid. However, modern architecture is based on non-Euclidean mathematical principles, allowing the architect to dream more and incorporate more creativity into their designs. This is the Nagakin capsule tower designed by the architect Kishore Kurukowa in Shimbashi, Tokyo, and it embodies the principle of modular architecture. Modular architecture refers to the design of a system composed of separate components that can be connected together. So here any one component can be added or replaced without affecting the rest of the system. So here each capsule is attached independently and then it is cantilevered from a shaft. So you can replace any one capsule without affecting the rest of the system. Geometric order is a mathematical principle that has been used by architects even in the ancient times to confer monumentality and importance. Especially in the design of the Gothic cathedrals and the Doric temple, architects have used this mathematical principle of geometric order to confer importance. The similar concept has been used in the design of the modern entrance to the Louvre Museum. Even though chaos and geometric order are completely opposite of each other, they are very closely linked because chaos helps to revive an architectural space. So this is an example of chaos in architecture because it gives you the impression of the random composition of different components. So this is the UFA Cinema Center in Dresden. If you consider the pattern in the Romanesco broccoli, in the fern and in the flowering of a dill plant, all these three have one thing in common. That is the repetition of a unique pattern in different scales. So this is the mathematical property known as fractals. So this mathematical property has been used in the design of the Sierpinski gasket and the Menger sponge. Architect Xavier Vivalta took inspiration from this mathematical principle in nature and the Menger sponge, and he designed the Lideta Mercato, which is the unconventional shopping mall in Ethiopia. So here he used concrete blocks with square cutouts to provide cross ventilation and natural lighting. So this is an example of where the mathematical principles found in nature has been incorporated into architecture to improve its appearance as well as its function. The golden ratio and the Fibonacci sequence are the blueprint of nature's design. So these mathematical principles found in nature has inspired ancient architects, especially in the design of the largest pyramid in Giza. If you apply the Pythagoras theorem to the golden ratio equation, you get the golden triangle. If you place two golden triangles back to back, you get the golden pyramid. And if you obtain the ratio of height to width of the golden pyramid, it is the same as the ratio of height to width of the actual pyramid in Giza. Not only in ancient architecture, the golden ratio has also been used in the design of modern architecture as well. For example, in the design of the UN Secretariat building. If you compare the entire width of the building and compare it to the height of every 10 floors, all of those rectangles are golden rectangles. And if you observe the image of the UN Secretariat building, you can see that it is made of 4 non-reflective bands. And it can be proven that each non-reflective band lies at a golden ratio point. So I obtained a frangipani leaf, then I took a picture of it and I imported it into Rhino 3D and I traced its pattern and I studied it for fractals. Then I found that there were fractals in its design. From each vein, a rectangular section is emerging, and from each of the edges, more rectangular sections are emerging, and then this pattern is repeated indefinitely to give the pattern of the leaf. So then I used that design, incorporated that design into a square of size 20 meter by 20 meter, and then to obtain the walls, I bent its edges. So this is the walls of the structure. So this was designed with 2 mm steel plates. So the intention was to export this file to SAP 2000 and to analyze it from there. But however, because of the incompatibility of the two softwares, I was unable to analyze the structure. So in conclusion, I can say that natural structures that stand the test of time can provide the same architectural sophistication and engineering stability when replicated. Thank you.
Okay. Now it's the question time. You can ask questions.
After doing the study, what is your main conclusion which you didn't know before you started the study?
I'm saying that in nature, for example, I took the leaf, right? So the leaf has, like, for millions of years, the leaf has been there and it can withstand the various types of weather. So I'm saying that the mathematical principles that nature has used, which are not the concepts that we incorporate into our architecture, we can go to nature, look at what are the mathematical algorithms that there are, and we can incorporate into our designs. So we can improve. For example, the Lidata Mercato, he has gotten natural lighting as well as ventilation from that. So I'm saying that we can look to nature to find other mathematical algorithms there and incorporate that into our architectural structures to improve its function.
So could you have said that before you started? No, you started the study because you thought that.
Yes.
So what did you conclude after your study which you didn't know before?
So when I started it, it was merely a question whether it could be done. So I think at the end of the research, I concluded it to myself that yeah, it can be done.
Now please just illustrate the natural shapes and process to your field.
Yeah, the principles.
So any questions from the audience?
So now you have analyzed a leaf, the fractals of leaf. So it is basically 2D in nature, and when you incorporate that pattern into a building, it is 3D in nature. So how do you deduce that you will get the stability of 2D into the 3D structure without analyzing the structure?
Yes, so to analyze it, I think if you design it by Rhino, you have to analyze it by using another software called Grasshopper. So because this is my final year project, so because of the time constraint, I could not study another software because Rhino 3D was also new software for me. I had to study it from scratch, and Grasshopper is a completely new software. So what I thought was I could import it onto SAP, which is a familiar software for me, and analyze it there. However, because like in SAP 2000, you can't draw curves and things like that. So when I imported this curve structure onto SAP, it was broken into infinite number of lines. So it was very difficult to analyze the structure because of that.
So your conclusion was that in 2D form now, the whole leaves has been undergone so many climatic conditions, so it is a stable structure. So that is in 2D form. It is even though 3D, but it is negligible thickness. But when you form it, when you using those fractals and form it to a 3D structure, how it would be? How do you perceive the stability of that? You understand my point?
I think design.
From the mathematical point of view, just to look at the three-dimensional objects, if one of the two-dimensional object is three-dimensional, what are mathematical algorithms over there?
So the similar concept has been used in the design of the Bellman Studio. So they have taken a mathematical principle, just a general mathematical principle, and they have drawn it onto a square, and they have just bent it and taken the edges. So I use the same concept which is used by the architect Bellman in the design of this.
I think the answer to it is that you can use these kind of concepts to design in architecture aesthetically. aesthetically, there will be aesthetically, but structurally to go with that withstand, you have to do so much with. I have another question. Has this been done by anybody else?
Not incorporating what is in nature exactly, because we can see Lideta Merca in the design of that, he has used what is the meninge sponge. That is not directly what is, even though the concept of fractals is in nature, and he has used the meninge sponge, which is, it is not exactly what is in nature. And even in the Balmain studio, they have used a direct mathematical algorithm, but I think this is different because I have taken it directly from a leaf. So it is not exactly a mathematical algorithm, it is what is found in nature.
Okay, so shall we do a hand gathering, please?